sorry, I was just looking for the microphone, but I don't know where it is in this room, so, oh well, hopefully you can hear me. I'll try to speak loudly. So I'm Kevin Leighton-Brown. I'm one of the AI faculty here, and I'm covering for Alan, who can't be here today. So I've taught this course for years, so I'm quite happy to tell you about decision theory. These are Alan's slides, so there might be some points where I'm trying to figure out what Alan meant by his cryptic slides, which I went over the last hour and found some a little bit mysterious, but we'll figure it out together. Let me start by some announcement that Alan asked me to make. So you've got an assignment that's due next Wednesday. You've got a list of short questions for the final online, which you're definitely going to want to look at. I'm sure I don't need to tell you that. He'd like you to suggest review topics on Connect, and he's giving you the last final. So a lot of exam preparation and assignment stuff for you to be paying attention to. And he's also posted some exercises and some auxiliary AI space materials. So is there anything about this that we should all discuss before we dive in and talk about decision theory? The excitement in the room is palpable. Okay. Oh, look, we have more evaluations. I mean, more announcements. The first one being about evaluations. So, right, so you had a chance to evaluate teachers, except for me. You can't evaluate me because I'm not on the forum. But you can evaluate Alan, and you should, because it's an important thing for the department. So you hear this from everybody, but it's really true. These evaluations, we pay a lot of attention to them. The professors eventually get your anonymized comments. They get the comments after they've given you your grades. So you don't have to worry that your grade will somehow be affected by the kinds of evaluations you give. We get them 2 months from now or something. But you can only submit them until before the exam. So don't forget. And you'll keep getting spam from UBC over and over and over again. Whether you submit your entries or not, as far as I know, you're just going to keep getting these irritating emails from UBC. But at least you can feel good about yourself that you did them. So, good. Okay. So here's where we're at. So as I understand it, you guys wrapped up reasoning under uncertainty last time, but didn't touch decision theory at all. Is that right? How many of you think that you wrapped up reasoning under uncertainty? Okay, so none of you. 2 people in the front. Is everyone else just checking Facebook, or what's going on here? Really? Yeah.
I'll answer that. Sometimes when you're dealing with a decision in decision theory, you aren't certain about all the facts or your facts. So
I wasn't even asking you to be certain about decision theory. You're ahead of the game if you know that. I'm just asking you to reason under uncertainty. But yeah, so I mean, help me out here, guys. You got to the end of that? Is there something more you need to know about that, or is it all good? Okay. So here's a big picture slide you've probably seen before. So I guess the dark blue stuff you've actually seen in class and should be familiar to you, and you should expect to hear more about it on the final exam. The light blue stuff, dynamic Bayesian networks, I guess you haven't seen. Is that right? You haven't seen it? You know what it is? Have you been told ever before what it is? Is this your opportunity to find out what it is? Maybe I should tell you what it is. So a dynamic Bayesian network is basically a Bayesian network that has time in it. So if you want to think about reasoning under uncertainty about some kind of process that unfolds over time, there are 2 things that you could do. One thing that you could do would be to make new variables for all of the different things that can happen over time, all the different stages that a random variable can get into as time unfolds. And then you don't have a problem, right? Then you just have an enormous Bayesian network with way too many variables in it. The problem is this would only allow you to think about some finite time horizon because you would have to unroll it some finite amount, and it would be terrible because it would be way too big. So the other thing you can do is to kind of take explicit concept of time, build it into your Bayesian network, and instead have kind of a Bayesian network that talks about how things unfold over time, and then really describes how one time step is sort of derived from the previous time step. So instead of saying, I'm going to tell a story about how some random process evolves for some short amount of time, I'm instead going to talk about how something evolves kind of indefinitely and be able to reason about whether something would happen at some point in the future. So that's what a dynamic Bayesian network is. I'm not going to tell you how they work because that would be a lecture or 2, But just want to tell you that there's a compact way of reasoning under uncertainty in domains where things change over time. So if that's a problem that turns out to be important for you at some point in the future, you know that it's called a dynamic Bayesian network, and you can go look it up, and you should, at this point, be able to understand it pretty easily based on what you already know. And all of these green things are just kind of cool applications of reasoning under uncertainty. These are the kinds of things people really use reasoning under uncertainty for. It's actually pretty widely used these days. So it's even sort of things as stupid as when you, on your computer, when Windows, something goes wrong and it says, do you want to run the troubleshooter? And it starts asking you a couple of questions. For each question, you can give some bulleted number of answers, or you can say, skip this question, I want to answer a different question. What you're actually doing is observing nodes in a Bayesian network. So they actually have built a Bayesian network based on fault data from other people's computers of what eventually turned out to have gone wrong. And it's actually reasoning under uncertainty about what might be wrong with your computer. So for kind of diagnosis style problems, these things are actually pretty widespread at this point. And I think you've probably seen this picture before. Have you? So here's a Bayesian network. It's really big. It can tell you whether you have liver disorder. Okay. That's all I have to say about that. So that's it for reasoning under uncertainty. Except it isn't really it for reasoning under uncertainty, because decision theory is going to turn out to build pretty directly on what you've already been doing. But now we're going to start thinking about decisions. So now we're going to talk about this thing called decision theory. And in particular, the way to kind of situate this within the plan of the class is that we're thinking about stochastic environments, so places where we want to represent our beliefs as being uncertain rather than being certain. You can, of course, either understand this as the environment itself is stochastic, or you can represent it as the environment may well be deterministic, but my own beliefs about it are uncertain, and so I might as well think that the environment is stochastic. About liver disorder, for example, you really do have liver disorder or you don't, but you're uncertain about which possible world you're in, and so you can think about it as being a random thing. So we're kind of in the stochastic column, and we're now in the, we're sort of straddling actually the sort of static and sequential columns, rows. He's drawn it here in the sequential row, but actually for much of today, we're going to think about just sort of one-step decision making, which in effect isn't really all that sequential, but it's going to, the same tools that we use for this one-step decision making are going to bootstrap pretty directly into multi-step decision making. Sort of much in the same way that planning, sort of one-step plans in a planning problem is sort of a static thing, but could easily be extended out. So today, the key thing, the key ingredient that today's topic is going to be about is saying, I've got beliefs that are represented using a Bayesian network, and I want to use those beliefs for something. I don't just want to know facts about the world that I can come up with probabilities and say, I think the chance that it's going to rain tomorrow, given that it's rained for the last 18 days in a row, is nearly 1. But I want to actually say, what should I do about it? Should I go to Whistler this weekend? Given the weather I see out the window, is the snow going to be good? The line's going to be short? And so I want to actually start using my probabilistic information to do something interesting, rather than just to kind of know something. So, indeed, earlier in the course, you've already been looking at decision-making problems. So you're thinking about, I've got some beliefs and I want to do something with those beliefs. You saw that with search and CSPs, which you can sort of think of as single-stage decisions in a sense. You saw that with planning. Planning, of course, is about making sequential decisions. In some sense, as you saw, search and CSPs leverage planning. So I might disagree with Alan a little bit that search and CSPs are really only about single-stage decisions. I think, as you saw with the way that planners actually work, they leverage both search and CSPs. And so in a sense, that's an enabling technology for both single and multiple decisions. Now we want to think about a stochastic domain where we've got these beliefs and you want to make decisions. And this is important because, as you've already really seen in just the belief representation work that you did before, it's a really powerful way of thinking about the world. Most of the AI systems that we build today have uncertain beliefs in them. And the reason is they just work better. They work better because the world is noisy. Things happen in the world that aren't in our models. They happen because sometimes there really is true randomness in the world. And they work well because they're more tolerant of misspecification. misspecification can get captured as noise rather than just being kind of causing the model to mismatch sort of fatally with reality. So in this kind of framework that we're going to talk about, an agent's decision is going to depend, kind of as always, on these three things. What actions are available to the agent to take, what beliefs the agent has about how the world works, what options are available to it, and what goals the agent has, what the agent is trying to do. Of course, we can't really talk about decision-making without talking about goals. Decision-making is fundamentally kind of goal-driven. It's saying, I have something I want to bring about, and I want to figure out how to make that happen. So the key thing that is representationally different here is that we're going to represent uncertain beliefs. And essentially, there's not much to say about that. We're going to do that using Bayesian networks. So you already know how Bayesian networks work. That's essentially going to be our answer to the middle of these three questions of what beliefs my agent has. So for a minute, let's talk about how we're going to represent actions and goals. Now, actions are going to turn out to be pretty straightforward as well. They're going to work essentially in the way that they did in planning. So I'm essentially going to have a variable that says, what choice do I make? And that variable is going to take a value that says what choice it is that I make, and that's going to correspond to my choice of an action. Goals, though, are kind of different. In principle, we could do the same thing that we did in planning, where we said, there's a thing that I want to achieve, make it so. Somehow orient the world in such a way that the thing that I wanted to have happen happens. But it turns out in decision theory, we do something richer. That in principle, we could have tried to do in planning, but we didn't. And that is to move, instead of just thinking about I have a goal or I don't have a goal, to thinking about something called utility, which is a measure of happiness. So I want to say the agent has what's called a utility function, which is basically a rating over all the states of the world that says how nice the agent thinks it is to be in that state of the world. And taking all three of these things together, the notion of kind of augmenting a Bayesian network with these decision variables and with a utility function, we're going to end up with something called a decision network. So now you guys are lucky enough to hear about the most sad and ridiculous AI example that I know of. It lives on in this course year after year, and it's so sad because decision theory is such a beautiful thing that is really practical, and this example is not going to make you think that. But the good thing about, obviously the tricky thing about examples is they have to be very small to fit on a slide, and it's hard to say much of anything that's interesting in an example that's small enough to fit on a slide, and that's why this one has the advantage that it does fit on a slide. But you don't, I think if you take this as kind of a funny thing rather than a sad and unmotivated thing, you'll be happier. So here's the story. I've got a robot, and I wanted to get from one place to another. And there are different routes that it could take. It could go, do I say this here? I'm going to talk about the second decision variable first. So it has a short route that it can take, which passes by the stairway. And there's a danger that the robot will sort of not control its motion very well and will fall down the stairway and be damaged. Or it can take the long way around the stairway. Now, as any sensible roboticist would do if they know that their robot is in danger of falling down the stairway, they could outfit it using padding. So they could put like hockey pads on the robot, so that if it does fall down the stairway, it isn't so badly damaged. But this adds extra weight and encumbrance to the robot in a way that uses up its power more, makes it less able to perform its tasks. So we've got two decisions to make here. Should the robot wear pads, and which route should it take? Now, generally speaking, this is kind of schematically a sort of decision that we make all the time, right? One decision is about, should I do something kind of safe and slow, or something fast and quick? That could be sort of like, should I speed in my car? Should I run the red light? Should I do something kind of risky and quick, or should I play it safe? And the first decision is kind of an insurance policy kind of decision. Should I take on some cost that I know I'm going to pay to kind of insure myself against a risk that may or may not happen? So schematically, this is a pretty reasonable example. I actually think the notion of a robot wearing pads is completely ridiculous, but that's just me. Okay, so then we've got a random variable here. And the random variable is, does the robot in fact have an accident, right? So we don't know from the two decisions that the robot makes whether there's an accident or not. If we did know for sure, then we would be back in the world of planning, right? There would be nothing uncertain going on here, and so the problem would be very easy. I could just kind of look at all the different outcomes and figure it out. But instead here, the probability of accident is going to be affected by the route that the robot took, and it's still going to be random either way. So one way to think about this is kind of as a tree. So I can say, first of all, I've got a decision variable here that says whether or not I should wear pads. Then I have a second decision variable, regardless of which decision I made the first time, that says which route should I take. Then I have a random variable. This is coming later rather than happening at the beginning because this random variable is conditional on the choice of route. So the chance of falling down the stairs is considerably greater if the robot goes by the stairs than if it doesn't. So we want to say that this random variable can be affected by the decision. You can think about that as being very analogous to a random variable being conditionally dependent on another random variable, except here it's being conditionally dependent on a decision that gets made. And then finally, we have 8 different possible worlds. Like good C programmers, we're going to number them starting from 0. And these are all the different things that can happen. So, if you wear the pads and you go the short way and you have an accident, there's moderate damage. If you don't wear the pads and you go the short way and you have an accident, there's severe damage. If there's no accident, there's never any damage. But whether or not you wear the pads affects your utility because you're carrying around this extra weight, and so on. So all of these kind of different things can happen. As you figured out, the green ones are a random variable that gets decided by the world. The red squares are places where the agent gets to make a decision. So I think we figured that out too. So possible worlds, sort of as you'll notice from this tree here, they tell us everything that can happen. They tell us how the random variable works out, but they also tell us what choices we made ourselves. So even though the decision variables are under our control, they're still part of the possible world. So that's why we have 8 possible worlds here. And something that isn't completely obvious, but makes a whole lot of sense if you think about it for a minute, is that you want to have the probabilities of the worlds that conditional on full instantiations of all the decision variables sum to 1. So in other words, once I've made all of my decisions, and then I look at all the possible worlds that are still possible based on the random variables changing, all of those different possible worlds should sum to 1. Now, you might think to yourself, shouldn't it be that just all of the possible worlds sum to 1? That's what you're more used to seeing. But of course, there's no randomness to my decision making. Right? I get to make my decisions any way I want. It would be kind of silly to say, wearing pads happens with probability 0.5, because I could say, well, no, it doesn't. I'm just not going to wear the pads. Take your 0.5 and shove it. I'm just going to, I'm making this decision here. So really the decision variables, because they're decided by the agent, they're not things that get probabilities associated with them. And so once I've made all my decisions in whatever way it is that I'm going to, I then face a random world, anything could happen. So I'm then in a situation where all the probabilities had better sum to 1. So we can start filling in some of these probabilities. So for example, this scenario here where I've taken the 2 upper branches in the tree, I might say that the accident happens with probability 0.2, no accident happens with probability 0.8. And I can similarly fill numbers in here. So notice that if you go the long way, it's very, very unlikely that you have an accident as compared to going the short way. Notice that the probability of having an accident is unrelated to the choice about wearing pads. We have the same accident probabilities again. So that's going to, we've done that in the example on purpose because we want to say that this choice about wearing pads is something that will affect my utility. It's going to affect how happy I am about different outcomes, but it isn't going to affect the random variable. It isn't going to affect which outcomes actually end up in. On the other hand, the short way, long way thing really does affect the random variable. So I've got one decision whose kind of major purpose is affecting the random variable, and I've got another decision whose major purpose is affecting how happy I am in different states of the world. Okay, so let's talk about this happiness. So utility, as I said, is a measure of how desirable different states of the world are. And it's formally we do this by saying we have a real valued function u, which is my utility function. And it's a mapping from possible worlds to numbers. Now, for some reason, Alan is setting this up to say that this number has to be on the range 0 to 100. Formally, it just has to be on any closed interval. So we've scaled to the interval 0, 100. 100 is not a special number here, but it is kind of a nice number, so fair enough. So we're going to here say that utilities are on this bounded range. So notice that this modeling change in saying that we're talking about utilities doesn't stop us from having this kind of goal-oriented perspective that we talked about before, because I could just do that by having only two utility values. I could say satisfying my goal is worth 100, or for that point of 17, so it's worth some positive amount. Not satisfying my goals are worth some smaller amount, say 0. And that's going to mean my agent likes being in worlds that satisfy the goal better than ones that doesn't, and otherwise it doesn't care about that. So that would put me kind of right back in that situation. But what's interesting is I can now say richer things as well. So it might be that the amount of damage, whether I got to the target, how much energy I used up, how much time I took, all of these things can kind of bake into my utility function. So kind of like the probabilities, these utilities kind of have to be given in the specification of the problem. So if I look at this example, I can ask, so actually there's something that isn't on the slide that's important to say, which is there's actually a theorem in utility theory, which is a little bit deep. It's actually kind of interesting. If you're interested in such things, I would check out the von Neumann-Morgenstern theorem of utility. If you're not, then I'll stop talking about it in a minute, but it's still interesting. And what this theorem says is that utility functions like this must exist. So utilities are not kind of just an assumption. They can actually be derived from something simpler, which is the idea that people have preference orderings. So if you have a kind of well-behaved preference ordering, then you must have a utility function. And this utility function has certain properties. One of the really important properties that this utility function has is that you feel the same about getting a certain amount of utility for sure and being in an uncertain situation where you get randomly different amounts of utility, but the average amount of utility you get is that same amount. So if I'm a decision theoretic agent is offered a choice between getting 10 units of utility for sure, or getting 5 units of utility half the time and 15 units of utility half the time, or getting 100 units of utility 1/10 of the time and 0 units of utility the rest of the time, anything that averages out to 10, they're all the same. The agent would be indifferent between all of those different things. So that's why here on the next slide we're going to start talking about the expected utility of actions. Because actually, when we're working with utility, that's the right thing to do. It's actually okay to treat expected utility as though that's just a sure payoff of that amount of utility. So, and so we have to think about expected utility here because we don't actually know what will happen with the accident node, right? So if I say, how much utility should I think that I'm going to get if I choose where pads equals yes, way equals short? So then, you would have to sort of ask me two things. The first is, how much utility do I actually get from these two possible worlds? And so I have to supply those numbers to you. So I'll say, you get having an accident in this scenario where you're wearing pads gives you a utility of 35, not so good. If you don't have the accident and you go the short way, but you're still weighed down by the pads, you lost a bit of utility, let's call that 95. So that's those numbers I have to supply to you. The other thing I have to tell you is, it looks like there's two numbers here, right? I'm hearing about the utility in two different possible worlds, but you're asking me about the utility just of making a decision. It sounds like you have a question that wants one number back instead of two. And that's the place where we want to take an expectation. So an expectation is like an average, but it's weighted, right? So I want to say, what is the weighted average of these utility amounts weighted by the probabilities of these possible worlds? So here the way I do that is I say, 20% probability of being in world 0, where I get utility 35, 80% probability of being in world 1, where I get probability at utility 95, do the convex combination there, and I end up with 83 units of utility. So that's how it works. The idea of decision theory is to say, making those two decisions, I get kind of 83 points for doing that. So I don't have to worry about the uncertainty anymore. The uncertainty kind of got rolled into this expected utility calculation, and now I can think about it sort of as though it's a sure thing. So now we can say that with math, and it says exactly what we just said, right? The expected utility of a possible world, given a probability of being in that possible world, is summing over worlds. The expected utility of kind of being out in the world is the sum over all the worlds you might be in. The probability of being in that possible world multiplied by the utility of being in that possible world. So expected utilities are just probabilities multiplied by utilities. Now, more often we're going to say, what's my conditional expected utility given some event? And that's just, I'm just going to take my probability condition on that event. And ultimately what we're going to use this for is the conditional expected utility of making a decision. So that's kind of what we just did. Okay, so I can write the expected utility of making a decision this way. So I can say the expected utility of deciding to say not wear pads and go the wrong way is this formula that you just saw. So I need to take all these conditional probabilities again, and I need to take these utilities now, kind of supply them all the way out. So here you see the rest of these utility numbers. And then I can compute the expected utility just by kind of grinding through these numbers, right? So I think I have more slides about how we grind through the numbers. So, but kind of intuitively, you should see how to do this, right? So if I want to figure out, say, this number here, I want to take this multiplied by that plus this multiplied by that, and it's going to give me this number. And in general, what that is the expected utility given a decision. So the conditioning on the decisions means that I'm in these possible worlds that are, I guess the conditioning on both decisions means that I'm in these two possible worlds here. And so then I just take the expectation of those possible worlds. Okay, any questions at this point? So far, so good. All right. So then, of course, when I've done all of this, what I really want to do is not just to kind of evaluate the values of different decisions, but rather to say, what decision ought I actually to take? So, given a single decision variable, I want to say, what's the optimal setting for that decision variable? What's the best thing for me to do? And of course, the agent can just choose any value in the domain of the variable. The optimal single-stage decision is kind of what you think it should be. It's whatever value from the domain of the decision variable that maximizes the expected utility. So just to walk you through this notation, remember that argmax is an operator that gives you back the argument that did the maximizing. So if I had said max here instead of argmax, it would tell me how much utility I get when I do the optimal decision. But argmax tells me which decision it is. And the reason that here we have a set membership operator rather than an equal sign is that it's possible that there will be ties. It's possible that there will be several decisions that all give me the same amount of utility. In that case, argmax is going to give me back a set. It's going to give me back everything that did the maximizing. And so the optimal decision is kind of anything from that set. So this is saying, from a decision theoretic point of view, if there's more than one thing that gives me the same amount of utility, I don't care which thing I pick. All of them are optimal. So there's a distinction which is, I think, more meaningful in this decision theoretic context than it was previously in the kind of reasoning under certainty context, between single actions and sequences of actions. So this kind of one-off decision scenario is one where you just have to think, work something out, and then act, and then you're done. And there's kind of no feedback from the action to the next decision to make. The reason why I think this, can anyone think about why I think this distinction is more meaningful in the reasoning under uncertainty kind of scenario than in the reasoning under certainty scenario? Those of you who aren't either asleep or checking your email? I can see some of you are doing both. Yeah, does anyone want to hazard a guess?
So
Yeah.
precisely what you said. Because the world is stochastic, we can expect feedback from a given decision, which is not going to, in reasoning under certainty, we're not expecting a particular set of feedback because our decision tree is basically, we can fall all the way down to the very leaf of our decision and know precisely what we'll get. In this framework, we can imagine a set of decisions which will then impact the world, and in particular impact the probabilities of the decision variables we will face subsequently.
So that's essentially right, but I wonder if we can be a little bit crisper about it. So it's true that kind of feedback is the key thing. So let's think about how feedback is really different, because you might kind of think, on the one hand, when you're reasoning kind of in a certain domain, you really are still thinking about something that unfolds over time, right? It seems like planning over time is still kind of a different thing from solving a CSP or something, right? On the other hand, it kind of does seem like maybe I have some feedback that I need to incorporate here. So can anyone else take a stab at why feedback is so important here? Well, what's really going on here is that in the kind of reasoning under certainty domain, I already know exactly what would happen after I took an action. And so I can kind of simulate the feedback that I would get in that scenario. And so there's kind of nothing, if I like, I can run a little simulation in my head of what would happen if I executed a plan, and kind of do all the reacting to what I learn in real time. Because I say, I take this action, I wonder what would happen. Well, I guess it would be this. And so then I would want to do something in that scenario, and I take another action, and then I know what would happen. And I can play out that simulation kind of reliably in my head. When I'm doing this reasoning under uncertainty thing, I'd say, I take the short route, and then, I don't know, I fall down the stairs or I don't. And the question about what the robot does in the next time step is going to kind of depend on whether I fall down the stairs. And I just don't know whether that's going to happen or not. And so, in a sense, I really need to wait to find out before I can do something else. So there is this sense of kind of learning something from the environment that I actually didn't know, which is how these random variables get realized. And that's something that I really didn't have as a problem before. That's why, I said that reasoning under, solving a strips planning problem or something seems kind of different from solving a CSP. That was sort of meant to provoke you, because as you've seen, it actually really isn't that different, right? You can actually encode it as a CSP. So although it feels initially like it ought to be different, you can sort of map it down. Here we're going to be doing something that we really can't just map down onto a CSP. And so there really is going to be something different about getting feedback and having to respond to it. So that's why right now we're going to think about making single decisions. It's because taking this feedback into account is actually trickier than it was before. So before we were able, as soon as we did planning, to just talk about sequential decision making, here we need to stop and be careful that we understand what decision making is about at all before we think about sequence. That being said, you'll notice the example we have today has two actions in it, so you might think there's sequence happening already. What's important is that after I take the first action, I don't actually learn anything. Right? I only observe my random variable after I've taken both of my actions in the scenario that I've given you, which means that there isn't really a meaningful sense in which they're different actions. So I can think about these two actions as really just being a convenient way of talking about a single decision that has 4 values in its domain. Right? So I decide these two things, at which point something happens. So although it's kind of, so that's why we have this sort of terminology of a one-off decision to draw a distinction between, it might not seem to you to be a single decision, but still to draw a distinction between that and sequential decision making. So sequential decision making, as I've kind of been alluding to, really involves this action observation cycle, which really is different from anything that you've seen before, where you make observations about what the world looks like, you decide on what to do, you do some reasoning, you actually do that action and change the world in some way, and then you repeat. So then you go back to sort of observing, seeing what you did to the world, reason about what to do, act again. So you're kind of constantly in this kind of control loop, which means that you're acting really without knowing what's going to happen out into the future. And in planning, that was just never the case. Planning was something where you could do all the thinking first and then all of the acting. You sort of wind up the little robot and you send it out on its way and it just does whatever it needs to do. So that's sort of fundamentally a different paradigm now, where you need to kind of keep checking in with the world to find out what's going on. That's all by way kind of setting up what we're going to do later, because right now we're still thinking about single decisions. So again, we're back to this kind of optimal single stage decision being one that maximizes expected value. So what is the optimal decision in this example? I'm told you have colorful little cards. Is this true? I want to see these cards for myself. I want to see this crazy educational technology in action. Right. Okay, I see like 5 of you with cards. Are you waiting me out? There will be more card choosing to come. So. Did UBC make you buy these cards in the bookstore, or did you get to make your own?
You gave us all the stuff.
Nice. It's included for free with your gigantic tuition bill.
Yeah.
Excellent. All right, so it looks like those of you who managed to dig out your fancy cards are mostly coming to the same point. I see 1 or 2 of you who are getting waylaid onto the wrong track here. So notice that the optimal decision is the one that gives me the highest expected utility, right? So this is kind of made easy because we've worked out all these numbers, we ground through all the math. That was kind of painful and annoying to do, but you can see how it wouldn't be so annoying for a computer. And so the finding an optimal decision problem really kind of amounts to the what's the biggest number problem, and you guys did a great job in taking the max of 4 numbers and picking 83. So, hooray, there it is. Okay, so although kind of that's the whole story for a single decision, notice that the only reason this was kind of easy is that somebody did all the math for you, right? If I had stopped kind of without the green stuff, it would have been a bit painful to figure out. And that's particularly true if we had much bigger domains, lots more random variables, lots more stuff going on. Reasoning about the structure of this whole thing would be kind of annoying. Notice in particular, these random variables might be structured as a Bayesian network. So it might be that to observe the random variable, it might be that you only care about action from the point of view of your utility function, accident from the point of view of your utility function, but maybe that's down at the bottom of a Bayesian network somewhere, and you have to do a bunch of inference to actually figure out what the probability of an accident actually is. It depends on whether the floor is slippery because it's raining, and whether somebody left the lights on, and all kinds of other random variables that make our example even more tortured. So what I want to think about now is algorithms for sort of extending the ideas we already have from Bayesian network inference to figure out what the optimal decision is. So to do that, we first of all kind of need a graphical language for talking about decision-making problems. And that's what we've got here. So this is called a decision network. And we've got the red squares and green circles that you remember. We really want to use this kind of multi-shape kind of vocabulary. This really is kind of a standard graphical language for thinking about decision-making problems. So we have square nodes, which are decisions. So these are things that I get to make. They're variables, so they're variables with a domain. But which value of the domain gets instantiated is up to me as the decision maker. Then we have the green nodes are random variables. So that's a choice by nature. So we're going to have conditional probability tables, as you've seen before, explaining how those get populated. And then we're going to have utility nodes that say my utility depends on all of the arguments that it takes. So I still have kind of a graph structure here that says the utility sort of cares about whichever values can come into it. But here, the table is going to be interpreted not as probabilities, but as utility values. So it's going to say, when all of these things jointly happen, here's how much utility I experience. There's always exactly one utility node. It doesn't have to have everything as parents. it only has to have as parents the things that matter for utility. So, for example, we could have set up this problem so that I don't care which way I go. That matters only for the accident probability. If I did that, there would be one missing edge in the graph, and I wouldn't have needed to have this edge. And you can see explicitly the dependencies. So before I kind of told you, and you might have believed me, or you might have looked for patterns in the number and kind of seen that it was true, that it seemed like accident really only depended on the route taken and not whether the robot was wearing pads. But that was kind of hard to see. Now that's something that is implicit in the, explicit in the graph structure. So we've got these three different kinds of nodes. I guess the only thing that we kind of don't already know about these nodes that I want to tell you on this slide is that the arcs going into the node, the decision variable node, represent information available. So you'll notice that our picture here doesn't have any such nodes. Because that's kind of what makes the problem sequential. You do something, you can imagine a situation where I take a decision, that affects a random variable, and then I make another decision that gets to observe the value of that random variable before the decision is made, and then I get some utility. That's what we mean by a sequential decision. And so this notion of being able to observe the value of a decision, whether that's possible, is something that's going to be indicated by incoming edges to a decision variable. So that's not something we're going to talk about today, but I just want you to understand that that's part of the semantics of the graphical language there. Okay. So to actually flesh out this decision network, I need to tell you what these tables are. So I can say, and so the way that these work, I mean, this one looks exactly the way you expect, right? It says, I look at the different values my parents can take, and then I have conditional probabilities, one for every value of my parent nodes. And I have one parent here, so there's one such thing. So my conditional probabilities sum to 1 for each value of my parent. The only thing that's kind of different here is that my parent node here is a decision node rather than a random variable, but I actually just don't care. I do it in exactly the same way. From the point of view of accident, it doesn't really matter whether which way is another random variable or a decision variable. It's some propositional variable that has some finite domain. So it just works out the same way. And utility just says, for every value of all of the variables that are incoming to it, how much utility do I get? So this doesn't have probabilities in the same way. It's just kind of a big table on the cross product of the domains of all of the different values going into it. And of course, we have no tables at all for the decision nodes because you get to pick. So there's kind of nothing to be said about that. Okay, so now I've told you pretty much everything except how we can use variable elimination to actually compute an optimal decision. And the answer is we do it pretty much in the way that you already would have done it. So once we set it up this way, we basically just use variable elimination again, except that we have to maximize at some point to find the best utility. So I'm going to denote my random variables as x's, my decision variables as d. I'll call the parents of a node n, p, a of n. And so the expected utility of acting in this world, following the optimal policy in this world, is summing out the probabilities of all of the random variables given the decision that I make, multiplied by the utility of the utility function evaluated at the parents of the utility function. And so then I can just kind of decompose in the usual way. And to find the optimal decision here, I'm going to create a factor for every conditional probability, and I'm also going to create a factor for the utilities. So this is another one of those reasons that we have this somewhat kind of confusing notion of factors in variable elimination, rather than kind of explicitly saying what these tables are. It's because we want to be able to smuggle in sort of semantically different things and just kind of call them tables and run the same steps on them. You've already seen that with sort of conditional probabilities, where we kept getting sort of different kinds of conditional probabilities, and they were just all factors. We didn't have to worry about it. Well, now that's even more true because we're going to have factors that aren't even probabilities at all. So we're just going to take the utility table and we're going to say, what the heck, that's a factor too. Everything gets to be a factor. So we're eventually going to sum out the random variables, And we're eventually going to end up with a factor on the decision variable that gives the expected utility of taking every decision. So running variable elimination here and summing out the random variables is just going to have the effect of building that kind of green vector that I gave you for free on the previous slide, so that you could just pick the maximum element from it. And then in the end, we pick the maximum element and we win. We've made our decision. So what you did when you guys voted was basically step 3. So what we want to do with variable elimination is steps 1 and 2, so that you build that thing that made it easy for you to make the right decision. So we start by creating these initial factors. So we say my expected utility is the sum over my actions of the probability of the action, given the choice of which way I go. And then my utility depends on whether the action, sorry, this is action, I keep saying action. It's probably an accident given which way I go. My utility depends on whether an accident happens, which way I went, and whether I wore pads. So I have these 2 tables, and so I just make factors out of both of these tables, right? So this is a factor in 3 variables, this is a factor in 2 variables, and so my expected utility is this sum over the 2 factors. So now the next thing I want to do is compute this product of 2 factors. And computing products of factors is something, you guys have been taking products of factors before, right? This should be well familiar to you at this point. And now this is kind of funny because one of these factors is a utility, but it just doesn't matter. We're just going to use that same product on factors operator that we already have. And so now here's another chance for you to use your fancy cards. So this question takes a little bit more thought than the previous one. What's the right form for this product? I have a grand total of 3 votes. Really, nobody else is prepared to vote here? Okay, that like doubled it. If I ask again, can I double it again? Okay, so those of you who are voting seem to be pretty much on the same page. Correct. So the pinks have it. So the domain of the product is the union of the products of the multiplicands. And so the way that I'm going to do this is kind of as a join, right? As it always was. It looks like you guys understand this. So I'm kind of running low on time. Let me see. So we kind of grind through this calculation in a way that really is just variable elimination, in a way that I hope you already understand. I'm going to spare you voting on that. So as we build this thing out, we really just end up doing that expected utility calculation that you've already seen. And really, I think from the point of view of today's lecture, where we're making a single decision, that's kind of all there is to it. What's going to be eventually helpful to us is that we can do this with more interesting structures, where things the decision variables themselves depend on random variables, where I might also be eliminating nodes in a Bayesian network so that I can observe what I need to observe to make my decision. Here we're looking at something so small that really I'm just taking the product. Unless there sure are a lot of slides about it. So I sum out the accident node once I have, once I've made this factor that has accident in it, I want to sum it out. I do that, again, kind of in the standard way, where I just have a factor, I want to sum something out of a factor. That's an operation on factors you had from before, and it works like it did before. And after having done that, I get a new factor now just in the decision variables, this F3 of which way I go and whether I wear pads. That's this factor here. And this is the factor that I showed you before that has these 4 numbers in it. And now I just want to choose a decision by taking a max across that factor. So I look at all of the different numbers in the factor, I pick the best one, I look at which arguments gave me that high value, and these are the arguments, and so that makes my decision for me. And I encourage you to play through this and other examples of making single decisions using AI space to better see how variable elimination works here. I think it's probably more rewarding for you to kind of do this interactively than having somebody read the steps of an algorithm to you. But I hope that this is making sense. I mean, really, so far, if you understood variable elimination in the case of probabilities only, this should really just look kind of the same. Once you understand that you pick the values of the decision nodes, the probability is conditioned on fully instantiating the decision nodes always sum to 1, and in the end, when you get this factor that involves only the decision nodes, you take a max over it. That's really the algorithm we've got. That's all you need to know. Things are going to get richer when we get to making multiple decisions, but that's going to be the topic for next class. I think that's kind of just what I said. This we're not going to say because the time permitting, and we don't have time to permit it. So I guess we have learning goals at the end. I don't want to take your time by saying this, but I think they'll be posted. But I will just leave these announcements up again in case you came in late. So thanks for your attention, and if you have any questions, I'll stick around for a few minutes now.